Section 250.122c of the National Electrical Code addresses the sizing of equipment grounding conductors when multiple circuits are installed within the same raceway or cable. The key principle is that a single equipment grounding conductor is permissible for multiple circuits if it is sized based on the largest overcurrent protective device protecting any of the circuit conductors within the raceway or cable. Let's consider the example provided. There are 4 circuits using 12 American wire gauge conductors and 1 circuit using 10 American wire gauge conductor, all running in the same electrical metallic tubing. In this scenario, Section 250.122c allows for a single equipment grounding conductor to serve all 5 circuits. The size of this equipment grounding conductor must be at least that of a 10 American wire gauge conductor, because the 10 American wire gauge conductor needs to be protected by the overcurrent device. This requirement ensures that the equipment grounding conductor has sufficient capacity to safely carry fault current back to the source, facilitating the operation of the overcurrent protective device and minimizing the risk of electrical shock or fire. Now let's delve into the topic of grounded conductors, also known as neutral conductors. The National Electrical Code generally prohibits the sharing of grounded conductors between different circuits. Section 210.4 of the NEC mandates that each circuit must have its own dedicated grounded conductor. This means that for every set of ungrounded conductors, there must be a corresponding grounded conductor that serves only those ungrounded conductors. The purpose of this requirement is to prevent unintentional current flow in the grounded conductor, which can occur if multiple circuits share a common neutral. Such current flow can lead to voltage drops, overheating, and potentially hazardous conditions. There are exceptions to this rule, specifically related to parallel circuits and multi-wire branch circuits. Firstly, Section 300.3b allows for the sharing of a common neutral in parallel circuits under certain conditions. Parallel circuits involve multiple conductors connected in parallel to increase the current carrying capacity of a circuit. In these cases, the shared neutral must be sized to accommodate the combined neutral current from all parallel conductors. Secondly, Section 210.4e addresses the use of shared grounded conductors in multi-wire branch circuits. A multi-wire branch circuit consists of 2 or more ungrounded conductors that share a common neutral conductor. These circuits are commonly found in residential and commercial buildings and are used to provide multiple 120-volt circuits from a 240 volts or 208 volt supply. The NEC permits the use of a shared neutral in multi-wire branch circuits as long as certain conditions are met. These conditions typically include the installation of a common trip breaker or fuse that will disconnect all ungrounded conductors simultaneously in the event of an overcurrent or ground fault. Additionally, the grounded conductor must be sized to carry the maximum unbalanced load. Understanding these requirements is crucial for ensuring electrical safety and compliance with the National Electrical Code. Equipment grounding conductors and grounded conductors play distinct roles in the electrical system, and it is essential to adhere to the specific regulations governing their installation and sizing. Firstly, equipment grounding conductors connect non-current carrying metal parts of electrical equipment to the grounding electrode system, providing a low impedance path for fault current. Secondly, grounded conductors, or neutrals, carry the return current from the load back to the source and are intentionally grounded at the service entrance. To reiterate, when installing multiple circuits in the same raceway or cable, a single equipment grounding conductor is permitted if it is sized based on the largest overcurrent device protecting any of the conductors. However, grounded conductors generally cannot be shared between different circuits, with exceptions for parallel circuits and multi-wire branch circuits under specific conditions. Always consult the latest edition of the National Electrical Code and seek guidance from qualified electrical professionals to ensure compliance and safety. Consider a scenario where you have 3 circuits running in a single conduit. Circuit 1 is a 20 amp circuit using 12 American wire gauge conductors. Circuit 2 is a 30 amp circuit using 10 American wire gauge conductors. And Circuit 3 is a 15 amp circuit using 14 American wire gauge conductors. According to Section 250.122c, You can use a single equipment grounding conductor for all 3 circuits, but it must be sized based on the largest overcurrent device, which in this case is the 30 amps breaker protecting the 10 American wire gauge conductors. Therefore, the equipment grounding conductor must be at least a 10 American wire gauge copper conductor, as specified in Table 250.122 of the NEC. Now let's say you have a multi-wire branch circuit supplying power to several lighting fixtures. The circuit consists of 2 ungrounded conductors, each carrying 120 volts, and a shared neutral conductor. The ungrounded conductors are protected by a double-pole 20 amps breaker. In this case, the neutral conductor must be sized to carry the maximum unbalanced load, which is the maximum current that will flow through the neutral conductor under normal operating conditions. If the maximum unbalanced load is 15 amps, then the neutral conductor must be at least a 14 American wire gauge conductor, as specified in Table 310.16 of the NEC. However, it's important to note that some jurisdictions may require the neutral conductor to be the same size as the ungrounded conductors, even if the maximum unbalanced load is less than the ampacity of the ungrounded conductors. This is to ensure that the neutral conductor has sufficient capacity to handle any potential future increases in load. It's also important to be aware of the potential for harmonic currents in multi-wire branch circuits, especially those serving nonlinear loads such as electronic ballasts and LED drivers. Harmonic currents can cause the neutral conductor to overheat, even if the unbalanced load is within the ampacity of the conductor. To mitigate this risk, it may be necessary to upsize the neutral conductor or install a harmonic filter. In addition to the requirements of the National Electrical Code, there may be local codes and regulations that apply to electrical installations. It's important to check with your local electrical inspector to ensure that your installation complies with all applicable requirements. Remember, electrical work can be dangerous, and it's always best to hire a qualified electrician to perform any electrical work that you're not comfortable doing yourself. A qualified electrician will have the knowledge and experience to ensure that the work is done safely and in accordance with all applicable codes and regulations. Also, consider the impact of voltage drop on the performance of electrical equipment. Voltage drop occurs when the voltage at the load is less than the voltage at the source due to the resistance of the conductors. Excessive voltage drop can cause equipment to operate inefficiently or even fail prematurely. To minimize voltage drop, it's important to use conductors that are large enough for the load and the distance. The National Electrical Code provides guidelines for calculating voltage drop, and there are also voltage drop calculators available online. When selecting conductors, it's also important to consider the type of insulation. The insulation must be suitable for the voltage, temperature, and environmental conditions of the installation. Common types of insulation include thermoplastic high heat resistant nylon coated, cross-linked polyethylene, and rubber. Thermoplastic high heat resistant nylon coated is a general purpose insulation that is suitable for most applications. Cross-linked polyethylene is a high-temperature insulation that is suitable for use in hot environments. Rubber is a flexible insulation that is suitable for use in damp locations. Also, be aware of the different types of raceways that are available. Raceways are enclosed channels that are used to protect and support electrical conductors. Common types of raceways include electrical metallic tubing, rigid metal conduit, and flexible metal conduit. Electrical metallic tubing is a thin-walled conduit that is suitable for use in dry locations. Rigid metal conduit is a thick-walled conduit that is suitable for use in wet or corrosive locations. Flexible metal conduit is a flexible conduit that is suitable for use in locations where the conduit needs to be bent or flexed. When installing raceways, it's important to follow the manufacturer's instructions and to use the correct fittings. The fittings must be compatible with the type of raceway being used and must provide a secure connection. It's also important to ensure that the raceway is properly grounded. The grounding conductor must be connected to the raceway at each end and at any intermediate points. This will help to protect against electrical shock in the event of a ground fault. In addition to the requirements of the National Electrical Code, there may be other standards that apply to electrical installations. For example, the National Fire Protection Association publishes standards for fire safety, and the Institute of Electrical and Electronics Engineers publishes standards for electrical engineering. It's important to be familiar with these standards and to follow them when designing and installing electrical systems. Finally, remember that electrical safety is everyone's responsibility. If you see something that doesn't look right, don't hesitate to report it to a qualified electrician. By working together, we can make sure that our electrical systems are safe and reliable. To recap the key points, firstly, a single equipment grounding conductor can be used for multiple circuits in the same raceway or cable if it's sized based on the largest overcurrent device protecting any of the conductors. Secondly, grounded conductors generally cannot be shared between different circuits, with exceptions for parallel circuits and multi-wire branch circuits under specific conditions. Thirdly, always consult the latest edition of the National Electrical Code and seek guidance from qualified electrical professionals to ensure compliance and safety. Fourthly, consider factors such as voltage drop, conductor insulation, and raceway selection when designing and installing electrical systems. Fifthly, be aware of local codes and regulations that may apply to electrical installations. Sixthly, electrical safety is everyone's responsibility, and it's important to report any potential hazards to a qualified electrician. By following these guidelines, you can help ensure that your electrical systems are safe and reliable. Let's consider some additional scenarios to further illustrate the application of these principles. Suppose you have a commercial building with multiple branch circuits feeding lighting and receptacle outlets. The branch circuits are run in conduit, and you want to determine the appropriate size of the equipment grounding conductor. You have several 20 amp circuits using 12 American wire gauge conductors, a few 30 amp circuits using 10 American wire gauge conductors, and one 50 amp circuit using 6 American wire gauge conductors. According to section 250.122c of the NEC, you can use a single equipment grounding conductor for all of these circuits, provided it is sized based on the largest overcurrent device. In this case, the largest overcurrent device is the 50 amps breaker protecting the 6 American wire gauge conductors. Therefore, you would need to select an equipment grounding conductor that is sized appropriately for a 50 amp circuit, which, according to table 250.122, would be a 10 American wire gauge copper conductor. Now let's consider a situation involving a multi-wire branch circuit in a residential setting. You have a 240 volt circuit with two ungrounded conductors and a shared neutral, supplying power to an electric range. Each ungrounded conductor is protected by a 40 amps breaker. In this case, the neutral conductor must be sized to carry the maximum unbalanced load. The maximum unbalanced load is the maximum current that will flow through the neutral conductor when one leg of the circuit is loaded more heavily than the other. In the case of an electric range, the unbalanced load can be significant, especially if one of the heating elements is turned on while the other is off. To determine the appropriate size of the neutral conductor, you would need to calculate the maximum unbalanced load based on the wattage ratings of the heating element. Once you have calculated the maximum unbalanced load, you can refer to table 310.16 of the NEC to determine the appropriate conductor size. In some cases, it may be necessary to upsize the neutral conductor to account for harmonic currents or other factors. It's important to remember that the National Electrical Code is a complex document, and it's essential to consult the latest edition and seek guidance from qualified electrical professionals to ensure compliance and safety. The code is constantly being updated to reflect changes in technology and best practices, so it's important to stay informed about the latest requirements. In addition to the National Electrical Code, there may be other standards and regulations that apply to electrical installations. These may include local codes, state codes, and industry standards. It's important to be aware of all applicable requirements and to follow them carefully. Finally, remember that electrical work can be dangerous, and it's always best to hire a qualified electrician to perform any electrical work that you're not comfortable doing yourself. A qualified electrician will have the knowledge and experience to ensure that the work is done safely and in accordance with all applicable codes and regulations. Let's explore the practical implications of shared neutrals in multi-wire branch circuits a bit further. Imagine a scenario in an office building where several computers and monitors are connected to a multi-wire branch circuit. Each computer and monitor draws a certain amount of current, and the neutral conductor carries the unbalanced current back to the source. If the load is perfectly balanced, meaning that each leg of the circuit draws the same amount of current, then the neutral conductor will carry very little current. However, in reality, the load is rarely perfectly balanced. Some computers may be drawing more current than others, and some monitors may be turned off while others are on. This creates an unbalanced load, and the neutral conductor must carry the difference in current between the two legs of the circuit. If the neutral conductor is not sized appropriately for the maximum unbalanced load, it can overheat, which can lead to a fire. In addition, harmonic currents can exacerbate the problem. Harmonic currents are currents that are at frequencies that are multiples of the fundamental frequency of the power system, which is typically 60 Hz. These currents are generated by nonlinear loads, such as electronic devices, and they can cause the neutral conductor to overheat, even if the unbalanced load is within the ampacity of the conductor. To mitigate the risk of overheating, it's important to size the neutral conductor appropriately for the maximum unbalanced load and to consider the potential for harmonic currents. In some cases, it may be necessary to upsize the neutral conductor or install a harmonic filter. It's also important to ensure that the neutral conductor is properly connected at all termination points. Loose connections can create resistance, which can cause the neutral conductor to overheat. In addition to the safety considerations, there are also performance considerations related to shared neutrals. If the neutral conductor is undersized or has loose connections, it can cause voltage drops, which can affect the performance of the equipment connected to the circuit. Voltage drops can cause computers to crash, monitors to flicker, and other equipment to malfunction. To minimize voltage drops, it's important to use conductors that are large enough for the load and the distance, and to ensure that all connections are tight and secure. In conclusion, the use of shared neutrals in multi-wire branch circuits requires careful consideration of safety and performance factors. It's important to size the neutral conductor appropriately for the maximum unbalanced load, to consider the potential for harmonic currents, and to ensure that all connections are tight and secure. By following these guidelines, you can help ensure that your electrical systems are safe and reliable.